Hello, in this very first video recording for my blog ModelAnalysis.ai, I'll walk you through the architecture of GPT-2 and I'll show you how to calculate the total number of learnable parameters for it. After that, I'll compare its architecture with LLaMA 3's so that you can see how similar they are. You'll gain more from this video if you have some prior knowledge in certain areas. But even if you don't have all the requisite knowledge, watching this video can still give you an appreciation of some of the core ideas that underlie transformers. Now, I've also written an article that makes a case for learning GPT-2. It also includes a few tips and links to other resources on how to get started. Links in the description. Okay, that's enough time with the intro. Let's get started. So I'm going to focus on the inference side of things as I go through this architecture. To start off, let's imagine that we have a sentence, the cat sat on the. When we feed this sentence into a tokenizer, it outputs 5 tokens. So there are 5 tokens here. Now tokens can be words or subwords. In this case, because these words are pretty small, they are each going to be broken up into corresponding tokens. So that's a space here. It's interesting that the second token is space CAT, not just cat. Third token is space sat, space on, space the. Now GPT-2 transformer uses byte pair encoding and there are 50,257 tokens. So every sentence that you input gets converted into one of those tokens. Now this is put through 2 blocks. Now each token is represented by these 2 types of embeddings. And each embedding is a vector of 768 numbers. This first embedding here represents the meaning of a token. The second one represents the position of the token. Now, both of these embedding vectors are learned during the pre-training phase of an LLM. So you have a matrix of 5 by 768. So 5 tokens, and for each token you have 767 numbers coming out of each of these embedding layers. So that's another 5 by 768. Now both of these numbers are literally added and that forms the very beginning of the residual stream. Now these are added rather than embedded, and it still boggles my mind that this works in deep learning. And as you go through transformers and deep learning in general, you'll see many such examples and you'll just have to get used to them. Why are we adding 2 numbers and how is that information retained? It's not entirely clear to me, to be honest, and I don't know how many people know this. Now you have transformer blocks stacked 12 times in GPT-2. So let's call this TF block. Maybe that's 1. And there are a total of 12 transformer blocks. And the residual stream, as it goes through each block, gets transformed twice. So what comes out here is X2 if you think about it. And given that there are 12 blocks, by the time you get out of this last transformer block, you end up with 24 times transformed residual stream. Now let me expand the transformer block, and when you expand it, you will notice that it contains an attention block and a transformer MLP block. So let's go through this. That's a residual stream XI. It gets modified twice. Now it goes through the layer normal form once, and you have, let's remember that that is the attention block and there are 12 attention heads. I will expand what these heads look like. There are 12 of them, and the output from this attention block gets added, and what you get is that's the first transformation. The output then goes through layer normal form 2, which is identical to this one, but the next bit is a simple straightforward feed-forward network, the output of which goes back and gets added to this residual stream. So that's essentially a skip connection to deal with vanishing gradient. So you keep the residual connection information and you add this additional bit, and what you get is 2 times transformed residual stream. XI plus 1, and XI plus 2. Now, let me talk about this layer normal form before I talk about the attention block and the MLP block. This block here plays an important role in training an LLM. It helps manage the vanishing and exploding gradients, and it contains two parameters, scaling and shifting, of the dimension that is equal to the size of the embedding, which is the 768. You will see why this is important when I calculate the parameter count. So the information is flowing this way and then comes back this way, then goes back that way, then comes back this way, then goes out as xi plus 2. Now let's look at what happens within each attention head, shall we? So this attention block here, this is the heart of the transformer architecture, and the main innovation of the attention is all you need paper. There are a total of 12 attention heads, as we talked about, and this means that the transformer block can pay attention to 12 different relationships. This also means that the transformer block can pay attention to different relationships simultaneously, and hence the name multi-headed attention. So let's take a look at what happens within each head. So the attention head each of the heads use what's called the KQV mechanism. So think of the input here as ln1 of xi plus 1. Sorry, xi. Let's just deal with that. So there you go. That's the layer norm applied to the residual stream. And that's coming out. You have Q, you have K, and you have V. Each of these attention heads are transformed or down projected from the residual stream into 1/12 of a matrix. Now each of these attention heads represent a particular part of the relationship. Now let's start with the query vector Q. It represents this particular relationship that each token is looking for. For example, in this particular attention head, maybe the token space SAT is trying to determine what the actor set action is referring to. Then you have the key vector that represents what each token is answering or offering. For example, in this case, it may be saying that the token pace cat may be trying to indicate that it's an actor of some action. And when the key representation of a token matches the query representation of another token, their corresponding attention probability ends up in a large value. So how do you calculate that? You basically take a dot product. The resulting attention score is softmaxed, and that resulting probability is then multiplied with the output of the value vector, and the linear transformation is then applied to this value vector, bringing the dimensionality back to that of the residual stream. Now let's talk about the MLP layer. This is a simple two-layer feed-forward network. The first layer, so let's get the residual stream, that's layer normed. So that's ln2 applied to xi plus 1. This is projected up into a higher dimension. So this number is 3072. Over here, it's a 768 dimension 1. And the activation function that is used in GPT-2 is GALU, Gaussian Error Linear Unit, I think. And then it gets projected down again, back to the same dimension that you would expect for the residual stream. So the residual stream coming out of the last transformer block is put through yet another layer norm. This one is identical in setup to the layer norms that we have seen here within the transformer block. And this normalized residual stream goes into the unembed layer. And the unembed layer is just a single layer that transforms the residual stream. Remember, it's always the same 5x768 stream that's making its way across. Now that gets projected into a bunch of logits, which are literally the scores of the possibilities of. So this is a 5 by 50,257. So the last token, the last representation here will show what is the most likely token that's going to come out of this, and that's going to represent the highest value. These scores are raw and unnormalized. They're converted into probabilities using softmax because it allows for sampling-based methods like temperature scaling. So let's do that. These are probs, and that's just softmax applied. GPT-2 uses these probabilities to calculate the cross entropy loss during the training. So that completes a quick walkthrough of GPT-2's architecture. Now, one of the things you commonly hear about LLMs is the number of parameters that they use. I want to show you how you can work out the parameter count for GPT-2. This way you can get a feel for what goes into these parameter counts. All right, let's copy that over here. Okay, so let's start off with embeddings because that's pretty straightforward. So we have 50,257 tokens. and each of them have 768 numbers representing the embedding. So that's 768. So you have 1024 positions representing the context length. That's the maximum number of tokens you can have in a sequence, and each of them is represented by 768 numbers. Now when you go to these layer norms, they have 768 scale parameters plus 768 shift parameters. That's the same here, 768 plus 768. That's the same here, 768 plus 768. Now don't forget that there are 12 transformer blocks here. Now, before I show you how to work out the parameter count for the MLP and the attention head, let me show you a couple of tricks that you can use to do this. When you multiply two matrices of shape M, N, and N and P, you get a matrix of shape M and P. It's as if the N here cancels out and what you're left with is M and P. So when you're projecting an input of shape MN into an output of shape M and P, you're multiplying it with another matrix of shape N and P, which is the same as here. That's N rows by P columns. That's a total of N times P weights as far as the neural networks are concerned, plus P bias terms. So the total number of parameters that you have to come up with this projection is N times P plus P. So that's the formula. Now let's go back and see how that works for the parameter calculation here. Remember, this dimension here is, for now, I'll just use the same blue color to show you what the residual stream has been. That's a 5 by 768 coming in. That's a 5 by 768 coming in. Now let's go back to red to show what happens. That 5 by 768 vector is being projected to 5 by 3072. It's being up projected. So you need to multiply to go up. You're multiplying this 5 by 768 with 768, 3072 parameters plus 3072 bias terms. Over here, the same 5 by 3072, and by the way, sorry, that should be a 2 there. Same 5 by 3072 is being down projected. So you're now multiplying it with 3072 times 768 with 768 bias terms. When it comes to each of these attention heads, and remember that there are 12 of them for each, each of them is an attention head, and there are 12 of them per transformer block. Let me go back to blue here to show you what's actually happening with this vector here. That 5 by 768 is down projected to 5 by 64, 5 by 64, and 5 by 64. And by the way, the way Q and K get multiplied is it's Q times KT. So that's the same as saying you end up with 5 times 64 times 64 times 5. So that's a 5 by 5. And then this 5 by 5 gets multiplied by 5 by 64, which is this 5 by 64 here. So what you get is 5 by 64, which has to be projected up into a 768 stream. So the projected up is what you have to end up with is 5 by 768. Just remember that when you multiply it with 12. So let's do the parameter count. In order for you to down project from this to this, you have 768 times 64 plus 64 bias terms. And remember, there are 3 of these for each attention head because there's Q, K, and V. And then over here, you're up projecting, and that is going from 64 to 768 with 768 bias terms. This happens at the attention block level at the top. So just to be clear, this layer normal form is 768 by 768. One last thing to call out is that this unembed here in many GPT-2 implementations, so far as I know, share the embeddings with the embed layer. So this is called weight tying. If you think about logically, it kind of makes sense because the token meaning should be the same when you're converting it into or out of the transformer. There are some implementations where that doesn't happen, but in most places they share the same parameters. So if you go back to the parameter count, you can see the way I've calculated these numbers, MLP, LN1, it's 12 times this for transformer block parameters. And then token embeddings, position embeddings, you don't see an embed here because these parameters are shared. So altogether, you end up with 124.4 million parameters. So as a last step in the video, I want to show you how LLaMA 3.1 8 billion parameter model compares with GPT-2. So for this model, the embedding size is 4096. And the vocabulary size, remember I said there are 50,257. Instead, there are 187,000 tokens. So any sequence of text you put in gets converted into 128,000 tokens. And the context length, if you remember, I said that the maximum number of tokens you can have in a sequence was 1024, whereas over here it's 128K. And what is the other big difference? Remember I said that the position embeddings are learned and they represent the meaning, or they represent each position. In LLaMA 3.1, instead of using learned position embeddings, rotary position encoding is used, and even that is not applied at the very beginning, but it's applied within the attention mechanism, and they aren't learned parameters either. So this is where rope is applied and you don't have this, okay? And instead of 12 transformer blocks, you have 32. And instead of having 12 heads per attention block, you have 32 attention heads. In terms of the attention, remember we're using QKV or KQV attention. LLaMA 3.1 uses grouped query attention, which is a variant of the multi-headed attention to reduce the computational cost while maintaining model quality. It modifies the multi-headed attention that you have here by reducing the number of key and value heads that you would have per the query head. So in summary, you have GQA here, which is a variation of the KQV that we went through already. So that's not used. Instead, GQA is used. And then instead of using GLU as the activation function, the LLaMA 3 family of LLMs use SWI-GLU as the activation function. Now, SWI-GLU is a portmanteau of swish and glue. So instead of GLU, we use SWI-GLU, which stands for, if I'm not wrong, swish gated linear unit. There is no answer to why we use SWI-GLU instead of GLU, other than to say that it seems to work. And finally, instead of using layer norms, LLaMA family uses RMS norm. Now that brings me to the conclusion of this video. It's possible that I omitted some important details or made a mistake or two. Please share your feedback in the comment section. Now, there are so many things I wanted to cover, but I was told that I'd be better off keeping the video to a manageable length. Let me know if you're interested in learning more details by posting in the comments. Thank you for watching.